3.6 optimization problems. Basically finding the best price for something or the largest area of an enclosure, things like that. Things we used to do in grade 10 using vertex form. We can now do using calculus. So example 1, just reviewing maybe a couple of steps, but what we're going to be looking for is details in the question, defining variables, adding a diagram if we need to, figuring out what the question is actually asking as far as the quantity that we're working with, and then we are going to need some functions or equations to talk about, and then we'll end up differentiating the function, talking about restrictions, and talking about critical values. So maximizing areas. Example 1, a lifeguard has 200 meters of rope. 200 meters of rope. She's going to enclose a rectangular area. You already have this diagram with the beach. So she's got 3 sides, 2 lengths, and 1 width will take up the whole rope, and she's got a buoy here and a buoy here to hold it in place, and maybe there and there. And the beach is going to form one side. Find the dimensions that will produce the maximum enclosed area. So area is length times width. And we're doing 2 different problems. A says no restrictions. No restrictions. And B, we're going to work with a restriction where the distance from the end of the enclosure to the beach has a max of 40 meters. That's for B. But for A, we don't have any restrictions. Okay, so we already have a couple of variables. We have A, L, and W. And so we're going to end up with 2 equations here. The first equation is pretty straightforward. It's A equals L times W. The second equation comes from the length of the rope. The length of the rope is 200 meters, and that is going to be 2 L's plus a W. 2L plus W. So if we have this 2 equations, but right now we have 3 variables, so we actually want to be able to express one of these variables in terms of the other variables. And so we look at equation 2 and we only have 2 variables. That's helpful because that means I can rearrange it. And for instance, I could express W in terms of L simply by subtracting 2L from both sides. So I'm going to do that. We've got W is equal to 200 minus 2L. So now I can go back into equation 1, which is our area formula. And everywhere I see a W, I'm just going to replace it with 200 minus 2L. So we have L times 200 minus 2L. So that looks like this. I should make my L's look the same so it's not confusing. Simplify, we end up with 200L minus 2L squared as our formula for area. So now we have a quadratic. We're kind of used to this from here. In the past, we would have gone to completing the square to get this in vertex form, which would give us the maximum area. So again, it's the L squared factor is negative, so this thing opens down, and we're basically looking for this point. But now that we have calculus, we know that we can find this point not by completing the square, but also by finding the critical points using our first derivative. So then the next step is to take the first derivative. I guess at this point too, we'd want to talk about the domain and range. So the allowable values for the domain is the values of L, the length, and length has to be greater than or equal to 0, but it's also going to be less than 100, because we have to at least get there and back, and if it was 100, that would be the whole rope, and if there's no width, then there's no area. So we've got L is, I'm going to put 0 here. L is greater than or equal to 0 and less than or equal to 100. Or we're looking for L values in the interval from 0 to 100. So that's the only restrictions that are on it, because that would max out our rope. So in section B, we'd be looking for L values between 0 and 40. But we'll worry about that when we get there. So taking the derivative of our area formula, A prime is 200 minus 4L. And now we're just finding the critical value, so we set that equal to 0. Subtract 200 from both sides. Divide both sides by -4. We get a critical value at L equals 50. That means there is either a max or a min at L equals 50. It's obviously a potential maximum, which gives us the L coordinate, and we still want to find out what the area of the enclosure is when L is 50. So that would be 50 by 100, right? 50 by 100 and another 50 there. Oh, can't even see what I'm doing. 50 by 100. So in order to get that, we take that value, we put it back into the original area function right here in terms of L. So we've got 200 times 50 minus 2 times 50 squared. And we end up with an area of 5,000 meters squared. Sorry. So I didn't really read the question very carefully. We need the dimensions, not necessarily the max area. So I have a length of 50, and then we need to find our width. So our width is 200 minus 2 times the length, which is 200 minus 100, which is 100. So there's our two dimensions, and we get a maximum area of 5,000 meters squared. And then we'd want to check that it actually is the maximum within the interval that we're talking about, so within from 0 to 100. There's a couple ways we can do this. You could test the first derivative to the left of 50 and to the right of 50. You'd find out that it's positive here and negative there. You could also take the second derivative, and you'd find out that the second derivative over this whole span is negative, which means it's concave down, which means the critical point is the maximum point. And the third option is just graph it, which is kind of what we did here. We know it's a quadratic, so it's a parabola, it's opening down, and so graphically we can easily determine that that is the maximum point. Yes, yes, maximizing area using calculus. In part B, we're doing the same problem, but this time our domain is restricted from 0 to 40. So our critical point was at 50. So if we're looking at 0, then 40 is going to be somewhere in here. Just by looking at it, we know that the maximum possible area is going to occur then at the bookend of our interval. So we don't need to do a ton of work to figure it out, because we know that we're increasing this whole interval from 0 to 50 and then decreasing after that. So if we're increasing all the way up to 50 and we have to stop at 40, then that's going to be our maximum point. So just with that logic, we know that L equals 40 will give us the greatest area over that interval. So then finding W when L equals 40, we just sub it in. It's 200 minus 80, which is 120. That's length and width. And we can get the area as well, which is just length times width. 40 times 120, which is 48 with 2 zeros, 4,800 meters squared. And these are meters, meters, maybe box your answers. There's the dimensions. Practice problems come from page 201. And you should be able to do, oh boy, a whole bunch. 1 through 20.